Welcome to Module 3, Biostatistics, Making Sense of Uncertainty. Statistics helps drive us to the most likely truth, and that's something that I want to emphasize. And I continue to encourage everyone to be curious and to dig deep into issues and look for best solutions when you're thinking about helping other people. And certainly in a world of uncertainty, and I would add a world where we have great access to a lot of information. Many times that information, uh, lacks context or what have you. And I'll give you an example. If you read a headline that says hospitalizations for COVID are up 50%, and no context is provided for that, nothing about who is being hospitalized, when they're being hospitalized, when the measurement of up 50% is done. So again, I want to encourage you to be curious and to explore what the truth is, and statistics is a great method to help us do that. So again, we're going to try to make sense out of uncertainty in statistics. So just a quick definition of what statistics are. It's a set of concepts and methods used to analyze data in the order to extract information. And we'll get into more detail here now in the videos that you will see on, we'll dig even deeper into the different methods in statistics. And it's a science, used to interpret the numbers and describe the health of the population. We have death rates, mortality rates. We have, we break people up by male and female, by race, by all these things, and statistics helps us do that and makes it better for us. So also makes the possibility of the translation of data into information, about cause and effects and health risks, and helps us cure disease. We're going to talk a lot about health risks, and if we're going to help populations, we have to help them properly interpret what their risks are, and statistics helps us do that also. Most science and research is probable in nature, and that's an important point to understand, that there is not absolutely like an A equals B, or very rarely in science. And then also something else that's really important if we're going to help the populations understand their risk is that the science of statistics can quantify the degree of uncertainty. So we'll look at risk and risk assessment as part of statistics here a little bit later, but it's important to be able to help people understand what their risks are. And I'll give you a quick example. My wife is a first grade school teacher. With COVID, she hears me talk about it all the time and talk about the science, and so she has probably a bigger risk tolerance than some other people have. And there's other reasons why they might have a great, or they may be more afraid of COVID. But she has one particular teacher that is just deathly afraid, and I feel bad for her. And she, I would suggest, does not understand her likelihood of catching COVID and then dying from COVID, maybe as well as my wife does. So we'll talk about the science of statistics and using it to help people better understand their risk. Again, probability. This is a key concept that we need to understand. The probabilities are used to describe the variety and frequency of past outcomes under similar conditions as a way to predicting what should happen in the future. So we will look at the calculation of a p-value, which is really a probability value is what it's called. And we'll see situations where it has like a 95, what's called a 95% confidence interval, which means the p-value is 5% or less. This is something that, again, it doesn't guarantee that there's a cause and effect, but it does give you a bigger probability, if you will, that is the case. Confidence interval, you see it in voting, in elections, where they say like 50% of the people support this candidate with an error rate or a confidence interval of plus or minus 3%. So it could be 47%, it could be 53%. So that's another important statistic that we will, take a little deeper look at. The power of a study. Now, this is really the theory of large numbers is that if you have, for example, if I flip a coin 5 times, there's a possibility, or decent possibility, I should say, but there's a possibility that I could flip 5 heads in a row, right? If I flip a coin 100 times, that possibility is less, and you'll get closer to, you know, one head versus one tail with an equal coin. And you're actually going to see a video in your module that kind of goes through that whole idea of flipping a coin and how that relates to, results that you can expect to get, and how the power of large numbers confers power. So let's dig a little bit deeper into the numbers and the terms that you will come across with statistics. The first one I want to look at is incident rate. Now, incidence by itself, not contemplating the rate, are simply like COVID are the new cases. And you've seen the bar charts that follow from, last March to now, where the bar charts show the number of new cases. So those people that have tested positive for COVID would be reflected in those charts. Prevalence are those that still have the condition, right? So they may test positive. They're going to go right into the prevalence because they have the current condition, which is COVID. Now, once they are healed and they have fully recovered, those people are going to fall out of the prevalence and no longer be in incidence or prevalence. So I want to look at common rates that are measured. Birth rates are obviously measured, mortality rates. I recently looked at a statistic that showed that the birth rates versus mortality rates in the US are actually coming down a little bit. It used to be like 2 births to every one mortality. This is maybe 30 years ago or so, but now it's more closer to like 1.5 births to 1 mortality. So even though our population continues to grow, it's not growing at the same rate that it was before. So those are interesting statistics to, not just interesting, but useful statistics to look at to determine if you're looking at, for example, population growth, how it impacts health. You've seen the pandemic COVID rates, cases, hospitalization, and mortality rates. All those are important for us in evaluating risk. Other rates commonly used are infant mortality rate and maternal mortality rate. So let's look at real quickly at what might be considered crude rates, and we'll compare that in a second to something that's more distinguishing, if you will. So this is a chart that shows the crude death rates for all causes. So as you can see there, it's around 900 per 100,000 in Q1 of 2019. And you can follow it along there. You can see as COVID came along that the 3-month periods, those deaths went up, which we understand now why. But what we can't distinguish here is we just know the number of deaths, right? We don't know if they're because of COVID. We don't know if they're what age group they might fall in. We don't know what the cause might be. So crude rates are not super helpful, and we'll see how we progress here so you can see more why as we expand to more adjusted rates that it becomes more and more useful. So here is a slightly adjusted. We've adjusted it for age, right? So we can see there that 85 plus are obviously dying the most, which makes sense in the sense that they're coming to the end of their lifespan. And you can see that the 1 to 4 year olds or 5 to 14, which is barely distinguishable, are ones that are passing away less. Again, makes perfect sense, right? But at least now we can make that distinction. So how do we make even further distinctions, right? So we adjust the rate and we apply now not just age, but cause of death, right? So now we have an additional bit of information that will help us get closer to a point where we can actually talk about an intervention. So I'll just look here to, if you look at the number one, and what this describes is 10 leading causes of death by age group. So we have the number of deaths here, right, which we had in the original chart. but that's all we had. We now have the age, which we had in the second chart, and the number of deaths. Now we have the name, or I'm sorry, the age, the number of deaths, and the cause of death. So we've expanded that and adjusted our information. So now we can you have some statistics we really do something with. And so let me just take one here. I mean, if we look at uh, let's look at the 15 to 24 category. We can see that the number one cause of death is unintentional injury. Certainly there are interventions we could do there. The number two cause of death is suicide. So that might be something we might want to take a look at and decide what sort of interventions might work there. If we go to the to the 65 plus group, the number one cause of injury is heart disease. So again, there are already interventions that are going on there, but whatever we can do, this information at least lets us know that we're focusing on the right areas and the most impactful areas, if you will. A couple other things that are calculated: life expectancy. Also in younger people, we will measure years of potential life lost. Again, going back to the suicide number, we might measure, but for suicide, number of years that were lost. I want to talk briefly about the statistics of screening tests. Some examples of some screening tests are mammograms, HIV tests, newborn screening, and COVID-19. So I want to talk briefly in the context of how tests are set up, sensitivity and specificity, the COVID-19 test. So the COVID-19 PCR test was set, I believe, at a cycle rate of, it went through 42 cycles to try to discover the virus. And so that's a highly sensitive, set at a high sensitivity, the PCR test. So what are you going to get when you do that? Because the idea of sensitivity is, you want to make sure that you produce a positive result for those that have the condition. So it makes sense in some ways that they set that as a high sensitivity. But it also will produce more false positives. So what's that end result when you set that high sensitivity? Is you are going to work hard to produce like all the positives that you're going to get, but you're also going to capture some if it goes through 42 cycles that have a very low viral load that may not even have the virus, but might just have one of the proteins that impacts or that might turn into the virus. So, and then in regards to specificity, this is how often do you correctly generate a negative result. So you want to make sure that you're producing when someone doesn't have the disease or the condition, you want to make sure that you have a specificity that makes it so more often than not, when they don't have the disease, the test results show as much. This is going to produce more false negatives. So someone might in fact have the disease when the test says that they do not. Want to talk briefly about lead time bias. This is like early detection of the disease, and I'm not suggesting that the early testing and that is not beneficial because I believe that it is. But in some circumstances, early detection is not going to extend the life of the patient. And if we take credit for that, might be improperly taking credit for that. But in like, for example, if someone has a certain sort of cancer, does early detection really lengthen their lifespan, or is their lifespan just extended, or their survival rate, I should say, number of years that they survive after diagnosis, is it higher just because we detected it early? And then I want to talk briefly about overdiagnosis bias. A good example is my father, who passed like 13 years ago. He had COPD, which was going to take him, probably had 3 or 4 years to live once he was diagnosed. They also discovered that he had prostate cancer. So they understood that he was going to go from the COPD before he before he went by the prostate cancer. So in that instance, they didn't treat the prostate cancer, and it was in essence an example of overdiagnosis bias. So risk assessment. This is statistics are so vital in helping us understand risk assessment. Um, you know, it identifies the exposures that might be harmful to humans, estimates the probability of occurrence, estimates the extent of harm that they may cause, uh, and we'll give you examples of each of these. For well-known risks, we can calculate from historical data. For poorly understand risk, may have to make some assumptions. COVID is not super well understood. Statistics are necessary to provide a picture of the risk and its severity and impotence. Now, this is important. Uh, I should say severity or impotence. This is important, and again, I'll use the context of COVID-19. Uh, so you've seen it. I've seen it. We talk about getting our kids back to school safely, right? And a lot of parents are like legitimately concerned that if they send their kid back to school, uh, that uh, their young child, would be at great risk uh, for COVID. And we'll go to the next slide here because it talks a little bit about that. So this is based on the data. This, I don't want to call it an assumption, but this perception that their child is at great risk by going back to school is driven by, in part at least, the misunderstanding of what the true risk is. And many people misinterpret risk. They'll, for example, I'll use COVID-19 as an example for a under 12-year-old person. There is statistically a 0% chance that that person is going to die from COVID, and yet we're concerned that we're going to send them back to school and they're in danger. And I'm talking about the perception of the parents, right? So what we can do as public health officials is try to help people understand, try to relieve some of that anxiety that they're misinterpreting, or that they're interpreting the risk and that the risk is not really what they believe it to be. So risk perception is classified in two separate areas: dread and knowability. So think about this for a second. So my risk of dying in a car accident is, you know, it's small, but it's not as small as me dying from COVID, right? But I know when I get on the road, I don't dread getting on the road because I know what the road is like. I've done it before, and I understand it, right? I understand those things, sort of things. So I'm going to interpret that as a low risk activity for me, even though it may be bigger than again death from COVID-19. Now let's talk about COVID. I dread it because I don't necessarily understand it, right? I don't know it. And so I might be more afraid, which I've seen a lot of people of that, even though my risk is sizably less than jumping in my car and going down the road. So one thing that I want to emphasize here is that again, through the use of statistics and just seeking out the truth, we can help people become less anxious about certain situations, right? And we're going to get more in Module 6 on the different models that we help use to try to mold behavior, or why people act the way that they do. And I think that's going to be helpful because, again, our ultimate goal here should be, how can we best help the most amount of people, right? And understanding that some people, again, misinterpret risk, and why they misinterpret it in us understanding that can help us, be more empathetic and increase the chance that they might change their behavior or their perception of risk than if not that intervention. There always is going to be like cost benefit analysis in things, and I won't spend a lot of time on here, but you know, this weighs the estimated cost of implementing a policy against the estimated benefit, usually in monetary terms. So, we're going to produce something like a cost per person, and what the benefit of that was, right? So we're going to essentially doing a cost benefit analysis just as it is to determine whether the output and the cost is worth the benefit that we think that we'll get. Again, costs are easier to calculate than benefits. Most, I should say, programs that you'll put into place as a public health official, or even just not as part of being a public health person, that you put in place, usually the reward is not realized until later on. The costs are realized up front, right? You pay for it now, and you realize that, and that's hard for a lot of people to have that sort of vision that yes, this can be happening. And again, we'll get more into the psychology behind that when we talk about human behavior in 5, in that uh, people also might not invest if they don't believe that they have the ability to be successful. So it gets intricate, but it's fascinating to me if we are able to understand all these things, that we can help more people. So here are just a couple of things that I want you to contemplate. Why are statistics, or is statistics, so important to public health? So nothing you have to write formally or whatever, but just I want you to think that through. And I want you to contemplate this too. I mean, think about a medical test that some of you that has undergone. Uh, was the test sensitive or specific, and why? What are the implications if the result were a false positive? Again, we talked about someone that, and this is an example, just one example, but someone that takes a pregnancy test and it gives a false positive, right? They're really pregnant, but it says, no, you're not pregnant. I guess eventually they'll understand that they are pregnant. And what if that was a false negative? The false positive would be, what are the ramifications, for example, of the false positive with COVID, right? Someone doesn't have it, and they are told that they do. So we're going to just dig a little bit deeper into more general terms. We talked about the numbers and how they work, but we're going to talk about just role in public health a little bit more. The use of data, you can read through these things, but essentially we're going to use it to assess. We're going to use it to research deeper certain diseases. We're going to be able to identify with data special risk groups. We're going to be able to detect new health threats, and we're going to be able to use this to plan programs like we talked about before. And also, it's going to help in preparation of budgets. Collection of data, birth certificates, death certificates, other vital statistics. And it's transmitted predominantly from through government, but there are some private, non-government agencies that also can provide data. The census provides us lots of great information on, male, female, race, age, all these things that are important to understanding what the makeup of our population is or are, and we can use that census. And there's some information here that you guys can access the census. And actually, there's a question here towards the end of this presentation that asks you to go in there and look at the census. National Health Interview Survey, again, all these links are going to be provided for you. I encourage you to go in and look at those and look at the different surveys that are being conducted by these different groups. Again, it's fantastic information. If we study it and we try to use statistics to get to the truth, it's invaluable. So how much data is necessary? There can never be too much data, and especially today that we have, and are progressing more on artificial intelligence, and we can go out and interpret the data for us. Really, we can't have too much data. Now, we can have too much bad data, but we cannot have too much data. Data is important in developing surveillance systems. And we've already mentioned this, collected by the agencies. Public health problems are defined by available data, and just the epidemic that we can't recognize it if we don't have the data. Data collection is imperfect. Census is the most accurate. And still, even with the most accurate, there still are variables to that, but hopefully it's within an error ratio that we can live with. And public health informatics has vastly improved it. Like I said, the amount of data and the way that technology has allowed us to organize it has helped public health and will continue to help public health because it'll continue to get better. Uh, and confidentiality of data. So this is always, or it will always be a challenge in that, people are not as likely to give up health information if you ask them specifics about themselves. If it is agnostic in that it doesn't provide your name, your address, all those things that would help identify you, then it's all great. But some people are going to be hesitant to give information because they think that you somehow are going to use that against them. But there's all sorts of protocols put in place where we try to make that information vanilla. That doesn't include any personal identifying information there. So here's again something I'd like for you to contemplate, and some of this stuff is available in the module itself. Here's what I'd like you to do: is visit the U.S. Census Bureau. Search what the population of your city or town is. How does it compare? How does the ethnic composition compare? And how does education level and population compare? So just be curious, go in there and spend 4 or 5 minutes and just try to see that information, see how you can access that information. And one more thing that I want you to contemplate is visit the NCHS website and look at the different surveys that they conduct, and just think about how they're beneficial and how these surveys might help translate into better health for the population. So there is a lot of great information in the slides, or I'm sorry, in the videos that you're going to see on, p-values, probability, confidence intervals, and risk assessment that you'll see after you see this video. So I encourage you to look through those, again, work through, what statistics is and how it can help you, better help the populations that you serve.